If you've ever built a recommendation engine, analyzed single-cell genomics data, or tried to compress a massive dataset, you've almost certainly run into matrix factorization. It's the workhorse of modern data science, because it lets us strip away noise and recover a low-dimensional structure hiding inside high-dimensional observations. But what happens when your data naturally lives in two distinct spaces, say, users and items or genes and pathways? That's where matrix Tri-Factorization comes in. Instead of splitting your data into two matrices, you split it into three, two outer matrices representing the distinct object sets, and a middle matrix capturing how they interact. It's incredibly expressive, but it comes with a brutal mathematical catch. Without extra constraints, Tri-Factorization is notoriously non-identifiable. That means there are infinitely many valid factorizations that perfectly reconstruct your data, making it impossible to guarantee you're actually recovering the true underlying structure. In practice, you're just rotating through an infinite solution space. Researchers have known for years that sparsity, the act of forcing most entries in these matrices to be exactly zero, acts as a powerful regularizer. In two-factor models, sparse recovery theory is rock solid. But for Tri-Factorization, the rigorous mathematical foundation has been almost completely missing. We've been using it successfully in the wild, but without provable guarantees, we were essentially flying blind about when and why it actually works. This research finally closes that gap. The authors developed a completely new mathematical strategy to prove when sparse Tri-Factorization is identifiable. Their key insight: instead of wrestling with the three-way split directly, they transformed the entire problem into two simpler, coupled two-factor problems. Think of it like taking apart a complex machine, isolating two of its core subsystems, proving they behave predictably on their own, and then rigorously showing that reassembling them preserves the original structure. This isn't just a computational trick. It's a structural bridge that lets us import well-established recovery theory into a much harder setting. So what does the math actually reveal? First, sparsity isn't just a practical heuristic. It's the direct driver of identifiability, convergence speed, and stability. The theory explicitly quantifies how the number of non-zero entries controls the algorithm's behavior. Specifically, they derive tight bounds showing that the sparsity level directly dictates the convergence rate of the optimization, the reliability of the latent interactions, and the overall error guarantees. In simpler terms, the sparser the true underlying structure, the faster and more reliably the algorithm converges to the correct factors. They also establish precise conditions on initialization quality and the degree of correlation required between latent factors for recovery to succeed. Every theoretical bound was validated against extensive simulations, and the empirical performance tracked the math almost exactly. But the real technical breakthrough lies in how they handle the transformation itself. When you map a Tri-Factorization problem into coupled two-factor subproblems, you risk distorting the underlying geometry. The authors prove that this distortion is tightly bounded. They track exactly how vector lengths, pairwise angles, and overall data stability shift during the transformation, showing that the essential geometric structure is preserved. This matters because similarity in high-dimensional data is fundamentally about angles. Their derivation proves that even after compression and transformation, the difference between true similarity and estimated similarity stays within a controlled error margin. That margin scales predictably with sparsity, matrix dimensions, and a tunable confidence parameter. They also look at how the transformation stretches or shrinks the data overall using singular values. You can think of singular values as the principal axes of your data cloud. When moving to a compressed latent space, you need to ensure you aren't accidentally warping those axes. The math shows that the largest and smallest singular values in the new space are strictly bounded. They can only change by factors tied to the maximum and minimum connection, strengths in the transformation matrices. This directly controls the condition number, the ratio between the largest and smallest singular values. A high condition number means numerical fragility, where tiny rounding errors blow up into massive mistakes. Their analysis proves the condition number stays tightly bounded after transformation, guaranteeing numerical stability even as data scales. And this isn't just asymptotic theory. They decompose the total error into manageable components: coefficient estimation error, dictionary shift between iterations, and noise interference. By bounding each piece, they show the total error follows a clean recursive pattern. Each step multiplies the previous error by a contraction factor strictly less than 1. That guarantees convergence. They even calculate exactly how many iterations are needed to reach a target accuracy, and show the probability of failure drops off exponentially as you scale up your data. To make this actionable, the authors built a complete algorithmic framework that pairs spectral initialization with iterative refinement. The algorithm alternates between estimating the coefficient matrices and updating the dictionaries, with sparsity constraints baked directly into the optimization steps. What's particularly valuable here is the practical roadmap it gives practitioners. You now have explicit formulas for how sparsity levels, data dimensions, and latent correlations interact to determine convergence. The rulebook is clear. Actively encourage sparsity in your coefficients, keep magnitude variations in check, and design your feature spaces to minimize unnecessary overlap. This framework doesn't just solve a theoretical puzzle. It provides a blueprint for extending these guarantees to more complex layered models. Ultimately, this research turns a long-standing practical heuristic into a mathematically grounded tool. By proving that sparsity induces identifiability in general real-valued Tri-Factorization, it gives us the confidence to deploy these models in high-stakes applications like drug discovery, knowledge graph completion, and neural network compression. We finally have the theoretical guarantees to back up what practitioners have been observing in the field. When you're working with massive, noisy datasets and trying to untangle hidden patterns, remember that the most reliable signal often comes from what's left blank. This work doesn't just give us better algorithms. It gives us the mathematical certainty that they actually work, paving the way for more transparent, robust, and theoretically sound AI systems.